טוב, אני... היו לי מחשבות לגבי מה שאמרתי לך, לגבי השיעור וקומפוזישן. אני בעצם לא מבין, הסתכלתי גם על התרגיל. אני יודע שאם יש לי, מצאתי מטריצה אחת, מקרה אחד שהוא כאילו מעניין לפי פולו. אוקיי? J. אני עכשיו יכול להראות שאם אני לוקח U טרנספורט JU, כשיהיו מטריצה אוניטרית, זה גם ייתן לי תוכן תכונות. מה עוד אני צריך חוץ מזה?
בשביל הדוגמה הזאת?
בשביל החיים.
אז יש לו עוד דברים אחרים בחיים.
מה יש עוד בחיים חוץ מהדוגמה הזאת?
אז יש את הדוגמה של non-normal amplification.
non-normal amplification זה אותו דבר. ראיתי דוגמה שבה יש לי משהו מעניין. עכשיו אני יודע שאם תעשה לי U טרנספורט של הדוגמה הזאת, אז אני אקבל את מה שאני רוצה.
לא, אבל מה אתה... מה התכונות של המטריצה שנותן לך את הדבר הזה ואת הדבר הזה, וגם זה שיש קשר
מה זה את זה?
את non-normal amplification או איזה delay line.
אני לא רואה למה השיעור לקומפוזישן תורם לי. אבל נדבר על זה, אבל אני חייב לדבר איתך על זה, זה מהר. נגיד בוא, 10 דקות. אוקיי. So, today we continue with attempting to understand working memory and integration. And I'd like to remind you that the examples that we discussed had a structure that looked something like the following. So in one dimension, tau r dot is equal to minus r plus jr plus external input. And we saw that when j is equal to 1, something interesting happens. That is, R becomes an integrator of the external input H. Now, the main motivation behind this question or writing these equations is first the behavioral finding that we have something that is called working memory, and that we can integrate inputs. And the most well-studied example is the oculomotor integrator that was extensively studied in the goldfish. Naively, this seems like a problem because the time scales of neurons and synapses seem too short to enable memory for seconds and tens of seconds. And one possible solution is through recurrent interactions. This is like the OTAPS example. We can increase the characteristic time of the network, and in the extreme case, result in an infinite characteristic time, which is infinite, and memory that can last in this framework forever. In practice, typically this would be seconds or tens of seconds. Questions about working memory? So, if I remember correctly, we talked about the OTAPS, and we talked about a system of 2 neurons. Now, the question that one would like to ask is what's the generalization here? What are the requirements from a general network? So let's consider the general case. So this would be writing the equations tau ri dot is equal to minus ri plus sum over j of jij rj plus hi0, or writing it in a vector way, tau r dot is equal to minus I minus j, where I and j are matrices, R plus H0 vector. So this is a general case. And the question is, what are the requirements on J such that this system or this set of equations can integrate input? Now, the generalization is anyone wants to answer this? Yes.
Some way J should be periodic.
Why should J be periodic?
No periodic, but the rules are periodization of each other.
Why should so you're talking about J that is periodic, or J that I forgot the name for these matrices where each one is I'm sorry? Is it circulant? I forgot. But why this would solve the problem? Why this is what you need? Well, I'll give you an example to show that you are wrong. Okay, let's consider what is arguably the simplest circulant matrix, or if this is the right name, all zeros. Okay, J is a matrix of all zeros, right? This would each row, each row is equal to each other row. They are all zeros, and then, well, neurons will converge will forget the external input within tau time units. So this doesn't seem to solve the problem. What was the trick when we talked about the two-dimensional case? You can look at your notes. One of the eigenvalues approached 1. So let's talk about this example, where what's the eigenvalue of this matrix? This is 1-by-1 matrix. The eigenvalue is J, and when J approaches 1, then this will become an integrator. Now, in the two-dimensional case, we also had an example. I can't remember whether it was the sum or the difference. The sum of the neurons, this was an eigenvector of J with an eigenvalue of 1. So that's a generalization. Any matrix J such that one of the eigenvalues approaches 1 can serve as an integrator, and well, one way of showing it is where we can write. If I write here, this is, you can still see it. So I'm going to write R, the vector R, as a linear combination of the eigenvectors of the matrix J, and we can write the external input also to be a combination of the eigenvectors of matrix J, which I will denote by Vk. And as we did in, I think it was the first or the second class, we can now write the dynamics of the coefficient, tau rk dot, and this will be equal to -1 minus lambda k, where lambda k is the eigenvalue corresponding, the eigenvalue of J corresponding to the eigenvector Vk. Or another way of writing it is tau divided by 1 minus lambda k rk twiddle dot is equal to minus rk twiddle plus hk 0 over 1 minus lambda k. And as before, when one of the lambda k's approaches 1, then then the dynamics will integrate the input in the direction of vk. So this is just a generalization of this simple example and the 2 by 2 example that we discussed last time. Questions about this? So there are several things that are worthwhile noting. One is the issue of fine-tuning, as before. Where do we see the fine-tuning? We have this term, 1 minus lambda k. So if lambda k is larger than 1, then the dynamics will diverge. Perfect integration will take place when lambda k is equal to 1. For smaller lambda k, well, let's say that lambda k is equal to 0.9, then the characteristic time in the slowest mode, in this mode, would be 10 times tau. If lambda k is 0.99, then the characteristic time in this direction would be 100 times tau. In order to explain behavior, we need something that is between 100 and 1,000 times tau. So we have this issue of fine-tuning of this matrix J. Another issue to bear in mind is nonlinearities. So far we wrote this set of linear equations. Remember when we talked about the rate model, the equations were nonlinear. We spoke about the sigmoidal function. And in order to justify using this set of equations, I used two justifications. First, I showed you data from the goldfish oculomotor integrator, and there the sigmoidal function is approximately threshold linear. And I said if we were only interested in the regime, in the linear regime, then we can write these equations. This is one justification. And second justification is, well, here we can do things. We can solve things. If it's nonlinear, it's all a mess. So it turns out that in order to construct something like this with nonlinearity, it is possible, but this is an additional challenge. Questions? So I would like to summarize things and say a few things about the biology. So from what we know about dynamical systems, so this is an example of a generic dynamical system, we expect that dynamical systems will converge in the absence, after transient input, the dynamics will converge to an attractor of the dynamics. And there are several generic, or there are three generic attractors that we know of. One is a fixed point. This is something that we discussed at length. Another attractor is a limit cycle, an attracting periodic solution. We considered one example of a limit cycle attractor when was it? What framework did we talk about the limit cycle attractor? Do you remember? Excitation and inhibition. So excitation and inhibition. A third attractor is a chaotic attractor. Strange attractor, the dynamics is chaotic, and we haven't encountered any such attractors yet. A fixed point attractor, one way of thinking about it is using the analogy of a Lyapunov function. I know that you can't always find one, it's more complicated and so on, but it's useful to think about a fixed point attractor as a minimum of some energy functions. So this would be an example of a single attractor, and more generally, if we have multiple attractors, and you can think about an energy landscape which is endowed with many minima. And you can think about this, I don't know how it's called, this thing where you buy eggs in. It has like multiple minima. So this would correspond to, if we think about the gradient-based dynamics on this, then it will have the minima of this shape of this energy function will be the fixed points of the dynamics. The attractor or the solution that we discussed, the one that appears on this whiteboard, is rather unique, and it's called line attractor or manifold attractor. And the idea is something like the following. If we use drawing, this would correspond to a situation where in one direction we have a continuum of fixed points, and in another direction or other directions, the dynamics converges to in this case to a one-dimensional attractor. This is not a generic solution that we find in nonlinear dynamics. You need fine-tuning in order to generate something like this, in order to generate a line attractor. So this, for example, would correspond to this set of equations. There is one direction in which convergence is fast, and there is one dimension in which there's no movement. So this is in this example, it is the sum that there's no movement along the sum, but there's fast convergence along the difference. And this would be this would be the architecture that will generate it. Now, this line attractor, so the reason that we learn these things is because we're interested in the brain and we're interested in biology. And let's go back to the problem of working memory. So we put the system in a state and it stays there. This is the experimental observation. So what kind of mechanisms can underlie this phenomenon? So one possible mechanism is the mechanism that we outlined here, something like a line attractor. Somehow the weights or the connections in the network are such that in one direction the dynamics of the neurons the dynamics become slow as a result of network interaction. That's one possibility. Another possibility would be that there is something intrinsically slow about the activity of the neurons. Let's say, I don't know, the ionic channels whose characteristic time scale is seconds, they respond slowly and they relax to a steady state slowly, and that's how the system maintains memory for seconds. Now my question to you is, how are we going to differentiate the two? What would be an experimental signature of one mechanism? This is something slow about the dynamics of neurons, compared with this mechanism. So how are we going to dissociate the two experimentally? What is the fundamental difference between the two? Let me try and clarify. Clearly, this set of equations does not characterize neurons in the brain. This is only an approximation. We use this approximation in order to characterize a possible solution to the puzzle of working memory and integration. Now, this understanding this mechanism is only useful if we can somehow relate it back to the experiments. Otherwise, I mean, maybe it's an interesting exercise in nonlinear dynamics, in this case in linear dynamics, but other than that, it's not very interesting or less interesting. My question to you is, what kind of experiment or what kind of observations will be more consistent with this scenario compared to everything is slow scenario? I'm sorry?
This also enables the fast decay in some cases, and in the everything is slow scenario, it will always be slow.
Okay, so if everything is slow, we expect that, well, everything would be slow. However, this scenario tells us something interesting. It tells us that if we consider one aspect of the neural dynamics, for example, the sum, the decay will be slow. Whereas if we look at a different projection of the neural activity, for example, a projection on 1 minus 1, then the dynamics will suddenly be fast. So the prediction of this idea of line attractor or manifold attractor that we will have slow relaxation, I mean, at some point, lambda cannot be exactly 1, so there will be slow relaxation, but it will only be in one direction. In the direction associated with an eigenvalue that is close to 1. In all other directions, we expect that the relaxation will be fast. And in fact, one way of testing it experimentally would be to perturb the neural activity in the network, and people have done it in the framework of the goldfish oculomotor integrator, and study the relaxation and signature of this mechanism is that there will be directions in which relaxation will be indeed fast. So this is just again the equation. So in this direction, relaxation is fast. Any questions? Now this is an important point because eventually we want to go back to the brain. We want to go back and understand how things work in the brain, and this is what we will look for if we think that the mechanism underlying working memory is a mechanism of something like line attractor. If we have a long biophysical time scale, then there will be relaxation in all directions. It will be slow in all directions. So this will be a signature of a fixed point solution with a slow relaxation. Questions? I would like to go back to the issue of structural instability. So the idea that small changes to the connectivity are expected to have a large effect on the ability of the network, to integrate. So, for example, presented in this illustration here, we expect that if lambda is slightly too small, then everything will converge to one fixed point here. Whereas if it is too large, then the dynamics is expected to diverge either in this way or from the center outwards, but it will diverge. The question is, how can we address this issue? So there are various possibilities of addressing these issues. This issue of instability, structural instability, and I told you about the fact that the ocular motor integrator of the fish works in more or less independently of the temperature of the water. I was looking for the reference. I couldn't find the reference showing it. One possible reference is common sense. I mean, fish live in different temperatures. I heard it from David Tank. I will keep on looking for the reference. I guess that these are things from the 70s and 80s. So one possibility, okay, so how are we going to deal with this issue of fine-tuning? One possibility is to constantly learn, constantly update, constantly learn the connectivity matrix. Some people have proposed this solution. Sebastian Sung is one of them. The problem then is it will work, but then you need to finely tune your learning algorithm. The learning algorithm has to be very precise in order to correctly update the connectivity matrix such that lambda will be very close to 1. This requires fine-tuning, not in the connectivity, but in the learning world. I told you about this issue of nonlinearity and the difficulty of constructing something like a line attractor when the dynamics are nonlinear. But it turns out that there is at least one example, one physical example, in which something like working memory works very well due to strong nonlinear interactions. I think it's an interesting example worthwhile thinking about. I'm going to put this eraser here. The location of the eraser has memory on the history of the dynamics. I could put it here, and I could put it here. This would correspond to different memories. Now, I'd like to show you that this system of memory is rather robust. It's not moving. Now, you all know it, right? I mean, it's not the first time that you encounter friction in your life. But think about it from a dynamical point of view. So the state of the system, let's call it R, can be what seems like at any point can stably attain any value. almost any value. And it is robust. Pretty robust. The question is, how does this work without fine-tuning? When you can think about it as a memory of an analog variable. So what is different in the physics of the interaction of this with a table compared with this interaction? Put differently, if we could understand this, maybe we'll understand how the brain attains or maintains a memory for periods of time which are much longer than the characteristic time of neurons and synapses. So what's the solution? So it turns out that the solution here is that the energy landscape looks something like this. At the microscopic level, the energy landscape looks something like this. As a result, the state of this system can attain many, many different points, almost a continuum of points. It's not a continuum, but from a macroscopic point of view, it looks as if it is a continuum. And because of this energy landscape, this system is robust to changes in, let's call it the parameters, as I demonstrated here. So this is an example where a continuum of solutions is maintained by a large number of microscopic fixed points that are very, very close to each other. And many people believe that, in fact, this is what underlies. This is a good analogy to the maintenance of memory. Questions? So now I would like to show you a small experiment that I did many years ago in order to test this prediction. I'll start with just a second. I'll start with a spoiler. The experiment failed. I failed miserably. Nevertheless, it was an interesting failure, and therefore I will present it to you. Yes?
What makes the system robust? How do we see it?
Well, okay, this is the energy landscape. Now I'm going to tilt it a little bit. So if I tilt it a little bit, I will get something that will look like this. Okay, but the minima are maintained. So the way to think about it is when I place this element here, this is the table. Okay, and this is the eraser. And when I tilt it, as long as the tilt is not too steep, it it is still stuck in these minima. That this would be the idea. It's actually the physics here is actually very interesting because it has been estimated that less than 1% of the surface of this object touches the table. Now, the question: what do we mean by touch? Becoming more complicated. But the issue of friction is a very interesting question in physics, and I think that better understanding this may help us understand working memory. That's my belief. But I'd like to go back to this failed experiment and what are the lessons that we can learn. So the hypothesis is that the energy landscape of working memory looks something like this. So let's draw it let's use MATLAB to draw it. So the idea is the following. Let's assume that this is the dimension of this one thing that I want to memorize. Okay, that's the dimension of the thing that I want to memorize. And now we can think about so I'm presented with one stimulus, or I'm presented with another stimulus. These will correspond to different stimuli. So if I'm presented with a right-hand stimulus, the memory will converge to this fixed point. Whereas if I'm presented with a left-hand stimulus, the memory will converge to this fixed point. So these are the multiple fixed points of memory. So to be precise here, the experiment is such that I will present to you bars of different lengths, and you have to memorize the length of the bar. So the idea, if memory is maintained by multiple fixed points rather than by line attractor, then maybe we can identify these memories because they are discrete. This is the idea. Questions? So this is the experiment presented with a bar. It disappears, and a second one, and okay. So how am I going to identify these fixed points? Well, in order to do that, I need to ask you, what did you remember? Right? I need to ask you, what did you remember? And the way that I'm going to ask you this question is by presenting you with another bar, and you will have to compare your memory with the current, with the presented bar. So the experiment looks something like this. You're presented with a bar, it disappears. Presented with another one, you have to say which one is longer. Let's do it. Which one was longer? Good. So in the experiment that I did, some of the stimuli were identical. So the first and second stimulus were exactly the same. There's no right answer here. So what's the prediction? What is the prediction of this model in the experiment in which the two stimuli are identical? Now the prediction is that if I present to you this stimulus, the first one, you memorize it as slightly longer than its veridical length, than its physical length. So in this case, you are predicted to report that the first one was actually longer than the second one. By contrast, if I present to you this one, just because of the structure of the energy landscape, you are predicted to report that the length of the first one is actually shorter than the length of the second one. Questions about the experiment? So now, if I have this energy landscape, then I can use it to compute the probability that I will report that the first one is longer than the second one as a function of the length of both of them. These are only an experiment in which the first one is equal to the second one. So if I can run a long enough experiment with enough stimuli, and if this is the energy landscape, then the prediction is that this is how the probability that the first one, this is how people will, or the subject will report about the probability that he will report that the first one is longer than the second one in those impossible trials in which the two lines are of identical length. Now clearly, this is not the right structure of the energy landscape. Well, I don't know, clearly. I don't know. And clearly, I cannot run an exhaustive experiment in which I use hundreds of trials or thousands of trials for every infinitesimal difference in length. So I cannot do this experiment, but I can sample this energy landscape in different locations. In principle, I can sample the energy landscape in different locations. And the prediction is that in some locations, I will see a consistent bias in one direction, and in other locations, I will see a persistent bias in the opposite direction. This is a prediction. Is the prediction clear to everyone? So what do you think will happen? So I'm doing an experiment. I'm presenting participants with lines of identical length. This is a prediction from this energy landscape hypothesis. What do you think will happen?
You said it fails.
Well, you can fail in many ways.
Something random like that?
What do you mean by random?
Not really chaotic, but not a bad.
Well, you cannot say chaotic because the word chaotic implies that things change in time. So I think it's a good exercise, what we're discussing now, because again, we're doing theory in order to go back and understand experiments. So I'd like to understand what are the predictions and why. So you said random or chaotic. Let's be clear about what you mean by that. So let's see what we can plot. So I'm going to plot. This would be the probability of reporting that L1 is larger than L2, right? As a function of L1 being equal to L2. So what's your prediction? Let's just for scale. This would be 0. This would be 1. This would be 1/2. This is chance. Okay, so round chance would be, let's say, I don't know, something like this, right? This is a round chance. Okay, just to clarify, what is it that I was looking for? What I was looking for is something like this. It will also look something like noise around chance, but it will have the following structure. So this would be significantly above and significantly below. So this would this would correspond to cases where by chance I fell, the memory was in the direction of underestimation, and these cases would be for cases in which the memory was in the direction of overestimation. The prediction was that this would be significantly different from chance. So one way of failing would be, well, everything would be on chance. This would be a prediction of this would be one possible failure from this prediction. Yes?
I missed something. If both lines are the same length,
Yes?
so that they converge to the same pixel?
No, because the first, it's a good question, but you have to memorize only the first one. The second one you see while you make a decision.
So the convergence to the fixed length is only for the first one?
Yes, because this is relevant. This is relevant time. It's in the memory. More predictions? So let's take a break and talk about the results right after the break.
כשאתה מראה את הדבר הזה, בעצם זה אומר שמלכתחילה אתה לא יכול לבחור את כל הערכים האפשריים.
נכון. אתה זוכר אותם רק בצורה דיסקרטית. כמו מחשב, ככה מחשב זוכר. העיקרון של מחשב הוא דיסקרטי.
לגבי עליית קולות, שהוא שעבר, דיברנו על lower bound. בכיתה אמרנו שהוא, במקרה שלנו הוא גדול לא שווה מ-0, שזה ה-lower bound שלו. זה לא צריך להיות תמיד חיובי, נכון? זה יכול lower bound יכול להיות גם שלילי?
כן, בעיקר שיש bound.
בעיקר שיש זה הולך.
שאלה על האינטגרציה.
אחרת אתה יכול, זאת אומרת אם אתה רוצה, אתה יכול להוציא קבוע.
זהו, זה מה שקרה.
על האינטגרציה במערכת הליניארית.
כן.
אז אומרים שכאילו אם שאר הערכים עצמיים הם שליליים, אז שאר המידע ממילא יידח, ואנחנו נשאר רק המידע שעליו אנחנו מבצעים את האינטגרציה. בדיוק. נכון, אבל אם המידע, אם האינפוט החיצוני מספיק חזק, הוא יכול להתגבר על הדעיכה הזאת, ואז גם יהיה לך עוד כיוונים שזה לא יידח.
נכון, אתה צודק, אבל אותו אתה תזכור לזמנים קצרים.
למה הוא לא יידח? אם הוא מספיק חזק?
אינפוט שהוא משתנה בזמן הוא קבוע בזמן? אינפוט שהוא משתנה בזמן. שמשתנה.
כן.
ברגע שאתה מפסיק את האינפוט הוא דרך אקספוננציאלי.
נכון.
שכח.
ברגע שנגמר האינפוט, הבנתי אותך, כאילו, equally, אוקיי. ואני לא. אמרתי, טוב, אולי זה לא, זה לא באמת. אבל עכשיו אני מקבלת את המתקפה כאילו מטורפת. אני לא אומרת, אני לא סבולת, אבל כולם כאילו לא בית.
אז אצלנו במקרה הזה שזה שלילי, בגלל הקבוע הזה של 2 או 2. אבל אנחנו לא צריכים אותו. מה שאנחנו צריכים שזה... מה זה אומר בעניין שלי? זה לא רק כלום, כי בגלל הקבוע. אני מסתכל על היחס פשוט כאילו בין... צריך שיהיה איזה lower bound. שזה יסתיים מתישהו, שזה הולך... כן, אבל למה אנחנו צריכים להיות גדול מזה? זה השינוי צריך... היה כתוב לי במחברת שאי גדול מ-0, אז היה כתוב לדוגמה הספציפית של לורנס אקוויישן.
y a un axe chez le moins Y dans lequel c'est sur le calcul qu'on a fait la dernière fois dans dimension 2, si tu veux, parce que là, c'est pas des vecteurs de dimension 2. Il y a un axe dans lequel ça décroît très rapidement, et tu rejoins sur l'attracteur, et il y a l'autre où ça ne décroît pas. C'est le cas en fait, tu sais, quand tu es sur la parabole, quand tu es en dimension 2, quand tu regardes la trace sur ce déterminant, disons que tu mets le déterminant en X et la trace en Y, en fait, c'est juste le point, je crois, cette ligne, les là d'attracteurs, en fait, ce sont des attracteurs
Okay, so let's close the door. So we discussed the prediction of a rough energy landscape in this simple working memory experiment, and so this was one possibility. So this was my dream. This is one way of failure. What other ways? Any ideas about the outcome of this experiment? So another possibility would be something like it's always above. Right? How would you interpret this result? Let's say that this would have been the answer. So you. But in a dynamical system, the framework of a dynamical system, how would you interpret such a result? What fixed point? So, for example, you would say that you have a fixed point which is in a location which is further away than the stimuli used in the experiment. The dynamics would convert to this fixed point, right? That's okay. So how would you test this prediction? Let's say that these are the results.
Multiple lengths.
I'm sorry?
Use multiple lengths.
So that would be one way of testing it. So the idea would be, so let's say that we have a fixed point here. So we expect that the longer wait between the stimuli, the further the memory will drift. And then the further up the point will go. This would be one way of testing it. Perhaps another would be to do an experiment with much longer lines. And maybe be able to go back to this fixed point. So that would be so the framework of dynamical systems gives us prediction that I think that we did not have previously about possible outcomes of experiments, and so it's worthwhile thinking about it in this framework. So these are the results. This is one subject, and what you see here is the probability that the subject will answer that the first one was longer than the second one as a function of the length of both of them. So when both lengths are short, subjects tend to overestimate the first one, and when they are long, they tend to underestimate them. So what would be the interpretation of this result? How should we interpret these results in the framework of dynamical systems? One fixed point, somewhere in the middle here. Okay. So the idea that there is a fixed point in the middle. So whenever we present a long stimulus, a short stimulus converges to a longer fixed point, and whenever we present a short one, it will converge to a smaller value. So how would you test this prediction of a single fixed point? The interval between stimuli. So the prediction is that if the interval between the first and second will be long,
We will be closer to the fixed point itself.
then the effect will become stronger. And well, you can say even something stronger, right? You can say that we expect that the convergence to the fixed point is exponential. So this tells you something about the rate at which you're expected, this function is expected to tilt with the interval. So it turns out that, at least in these experiments, changing the interval has almost no effect on the function. I went from half a second to 16 seconds. 16 is horrible as a subject. Maybe shorter. With shorter you have the issues of fixation point and other issues that enter. So one possibility is that you're already saturated. But if you are saturated, you would expect a step function, and not something that is analog. But things are worse because if you change the range of stimuli that you use, this center point also changes. This seems inconsistent with our framework that states that there is a single fixed point. So this framework doesn't seem to be, or these results don't seem to be, fully consistent with the idea of, to say the least, are not consistent with the idea of multiple fixed points. And actually, this is something that people have looked in other systems as well. They looked for discrete attractors in the goldfish ocular motor integrator. So they looked both at the neural activity, whether you see that it attains discrete values, or the location of the eye. In other systems, we don't find this energy landscape. I think it's still interesting. I mean, there are ways of explaining these results, but this is the way that these results can be explained. This is in a cognitive computational framework, not in a dynamical framework. And the lesson, I think, from this exercise is that things are more complicated than they seem. Even this very simple task, the two-line discrimination, is in fact something very, very complicated. Okay. I would like to go back to models of working memory and integration and describe alternatives that people have discussed in the literature. I will be more brief about alternatives. So let's use notation. So this will be one neuron. So one solution that people have discussed is the following. What if there are neurons in the brain or mechanisms in the brain that can compute the temporal derivative? So we have this neuron that can compute the derivative of the activity of this neuron. So a neuron that receives input from this neuron computes the change in time of this neuron. Mechanisms are mechanisms for adaptation. So it is not sensitive to the input, but only to changes in the input. And then the dynamics of this neuron, tau r dot is equal to minus r plus j times So this neuron inhibits this neuron, and the strength of inhibition is dependent on the temporal derivative. So then the dynamics will be tau plus j r dot is equal to minus r. That's as external input for the So if this J is sufficiently strong, then the decay of this neuron will become very slow. Put differently, the characteristic time of this neuron with this interaction is equal to its intrinsic time scale plus the strength of the connection from this neuron. And the stronger this J, the slower will be the decay of this neuron. So this is like these circuits are known in a control system. So this is a way in which the characteristic time of this neuron can increase to arbitrarily large. Yes.
Can you please draw it again in blue?
What? Everything? So this is a nice idea. It also relates derivative with integration. What's the problem here? Where is the fine-tuning hiding here? Well, it doesn't have to be finely tuned. I mean, let's say that J is 10,000 times tau, to keep the right units. Then, well, what do you care if it's 10,000 or 20,000? Still works pretty well. Fine-tuning is hiding here. How are you going to compute the derivative with perfect accuracy? So you can imagine the situation in which, even in the absence of change, the derivative gives you a reading of a change. So this is where the fine-tuning is hidden. Questions about the mechanism? The third mechanism that I wanted to describe to you is integration using a feed-forward architecture. So the integration that we discussed here was done by tuning the recurrent connections. In recent years, some people have proposed that working memory and integration occur in feed-forward rather than recurrent networks. Mark Goldman is one of the people who came forward with this idea. And to explain it, I will use a simple example that actually is simpler than the differential equations that we're talking about. So consider a case where we have a feed-forward network of neurons. And they're all connected to each other with an excitatory synapse J, the same J. And as a first step, we will consider simplified dynamics. The activity of neuron I plus 1 at time t plus delta t will be equal to the activity of neuron I at time t multiplied by the synaptic strength J. And the first neuron receives input the input is the first neuron is a neuron to receive external input. So this will be neuron 1, 2, this will be neuron N, and there's also external input to this neuron. Finally, I will assume that there is a readout mechanism, a neuron that receives input from all neurons in the network. Did they use R? Let's use, I want to be consistent with notations. Let's call everything R. I apologize. And this would be the output neuron. We just sum the activity of all neurons in the network. So how does this network behave? Well, the neuron at the first time point receives external input. This external input is propagated in the next time point to the second neuron, then to the third, then to the fourth, and to the fifth, until it reaches the last neuron, and then it falls out. The output neuron sums the activity of all neurons in the network. So when J is equal to 1, or even let's talk about the general case. So the output activity is just equal to the sum of inputs will sum over all neurons. Each one contributes the external input in time t minus I. I'm sorry? Sorry? With weighting, what would be the weighting, J? Summing over all neurons. J to the power I minus 1. So the first neuron, which encodes the most recent information, is not weighted by anything. This one will be weighted by 1J, 2J, 3Js, and so on. So when J, if we assume that J is equal to 1, or for J being equal to 1, then our output is equal to sum over I from 1 to n, the external input t minus I, I'm sorry, I times delta t. It should be delta t. Which is equal to 1 over delta t, an integral from t minus n delta t to t So if J is equal to 1, then this network maintains memory of the n external inputs. The output, being the sum of all the activities of all neurons, is the sum of all the external inputs in the last, or the sum of the last n external input, which is asymptotically equal to the integral over the external inputs. So this is the way in which a feed-forward network can integrate inputs for a limited period of time, where the period of time is determined by the number of neurons in the network. The larger the number of neurons in the network, the more, the longer the time period in which the system can maintain memory, and it's easy to conceive a network with 1,000 neurons, which enables the dynamics to maintain memory for 1,000 time periods of the neuron. Questions about this example?
Is there a dot in the R of T?
Sorry. No.
Okay.
You just sum. Basically, you just sum.
Yeah, you just send
Where?
Yeah.
Oh, this is just out. Questions about this example? So in order to come up with this example, we needed to assume that everything is discrete, the time is discrete. So we gave up on the differential equations. question is, how are we going to implement this idea in a feed-forward network using the standard rate model, or at least the linear version of the standard rate model? What would be the relevant equations?
Take n very large.
I'm sorry?
Take n very large.
Okay, but well, in this framework, we can take n to be equal to 2 or take n to be equal to 2 million. Conceptually, the results will be the same, just that the effective timescale of the network is equal to the number of neurons in the network times the characteristic time of the single neuron, which determines this delta t. What's the right discretization in time of such a network? But now I would like to do it using the differential equations. So what should I do? What would be the continuous time version of this one? Well, we don't have too many degrees of freedom. This is a standard model. But how should J look like? Thinking about this analogy. Can you say it again?
Diagonal of J below the main one.
Something like this. So everything here is J and everything here is 0.
All 0, but all 0, but the diagonal 1 below the main.
Something like this. Okay. Right. So this would be the analogy. What are the eigenvalues of this matrix? So this is a triangular matrix. Sorry? Zero. This is a triangular matrix. So all eigenvalues reside or are on the diagonal of the matrix. This is something we know from linear algebra. So clearly, we shouldn't expect the long time scale to be the result of the eigenvalues as before. But let's see how this let's see how this network would behave. For reasons that will for reasons of notation, I'm going to flip the labeling of the neuron. So the first neuron is going to be I'm going to denote it by n, the second one by n minus 1 until neuron 1. So now what we need to do is to compute the dynamics of each of the neurons. So let's say that we that there is a delta function input to the last neuron. So if the response, the entire network starts from being equal to 0, and there is a delta function input to the last neuron. So the dynamics of the last neuron, tau r n dot, is here. This is easy. It will be equal to minus Rn. Or Rn of t is equal to Rn of 0, e to the minus t over tau. Okay. This was easy. What about the second neuron? What can you say about the second neuron? So tau Rn minus 1 dot is equal to minus Rn minus 1 plus Rn. So Rn minus 1 t is equal to Rn minus 1 times 0 e to the minus t over tau plus 1 over tau integral from 0 to t e to the minus t minus s over tau Rn of s ds. And we can replace the Rn of s with Rn0 e to the minus s over tau and if we do the integral, the result would be t over tau e to the minus t over tau. So this would be now we can move to the next neuron. Tau Rn minus 2 dot is equal to minus Rn minus 2 plus Rn minus 1. And the way to do it is exactly as before, but this time we need to plug this one in the integral. And I leave it to you as an exercise to show that this will be equal to 1/2 t over tau squared e to the minus t over tau. And one can prove the general case R n minus j of t will be equal to 1 over j factorial t over tau to the power of j e to the minus t over tau. Everything here should be multiplied by Rn of 0. I will assume that Rn of 0 is equal to 1. I forgot to add the Rn of 0. So again, we consider a neuron, a readout neuron from all these neurons that sums the activity of all the neurons in the network. So this neuron is just equal to the sum of the activities of all neurons in the network, which will be equal to e to the minus t over tau times sum over j of t over tau to the power of j times 1 over j factorial. This is sum to n. Call the first neuron 1. So what is this sum? Sum over j, 1 over j factorial t over tau to the power of j. It's almost true. When will this be true? In the what goes to infinity? So the limit of n go to infinity of sum over j 1 over j factorial t to the power of tau, t over tau to the power of j is equal to e to the t over tau, and the limit of n goes to infinity, our output will be equal to e to the minus t over tau times e to the t over tau, which is equal to 1. So there was a delta input to this neuron, and independently of time, the output of the network is exactly this input. Now you can think about any input as a sum of delta functions. And because these equations are linear, the activity of all neurons in the network is just a sum of of these inputs. So the sum over all activities in the network will integrate all the inputs that the first neuron received. So one question that you may wonder about is, this is weird, because in this example, memory was maintained until only for n, memory was maintained for n time points. The integral was over n time points. And here, n is no longer present. So what's going on? So we were only able to do it when we took the limit of n to infinity. So, okay, but let's assume that n is large but not infinity. Let's say that n is 1,000 or 1 million. How long will this network be able to store memories? Okay. Or let's put differently. What would be t for which the network will still be a good integrator? The intuition from here tells us, that this should be approximately equal to n time delta t. So we expect that this would also be true, or this would hold when, as long as what? As long as t is smaller than, well, tau is not interesting. This is what you expect for one neuron. N times tau. So the intuition tells us that this should work pretty well for a t that is smaller than n times tau. On Thursday, I will prove it. It's actually pretty straightforward. I'll start Thursday with proving it. Questions? So we'll stop here.
jours après, là, ça peut être. Comment on está fuera? Una cosa che sono apprendere con bisogno. Sur le chaud, quoi. Négatif. C'est la dérive négative. Mais pas que, elle-même soit positive. C'est sympa la table. C'est sympa.
Bah, au lieu de dire I, j'ai dit J.
Ah, d'accord. Ah, ok.
Non, mais
je crois que des I.
Mais oui, non, mais
pas
oui. Ok, donc c'est la même chose. Et donc en fait, le problème c'est que dans l'intégration, il faut juste voir, parce que j'ai un résultat, mais donc c'est extensif en N, mais c'est pas tout le temps négatif. Mais le problème c'est que, je peux te montrer, mais en fait le problème c'est que j'ai montré l'intégration, parce que l'intégration en fait il faut faire attention, parce que parfois c'est plus simple, produit, parfois c'est moins 20. Mais il faut juste faire attention à quand, tu vois. Et j'ai mal fait attention à quand.
Mais juste une question dans le résultat que tu trouves, parce que moi je serais ravi d'avoir du sigma, du truc comme ça. Le problème c'est que, bon, déjà ça je pas, ça. Mais surtout, toi, ça diverge avec ton bêta vers 0 après. Une fois que tu as le résultat final, et tu fais tendre bêta vers 0. Vers l'infini, pardon.
Cosinus hyperbolique.
T'as du bêta carré, donc si tu fais tendre vers l'infini, ça va diverger.
Exactement.
Alors que.
Mais ça, de toute façon, a priori, ça c'est faux. Moi, ma question c'est.
Et il faut que ce soit négatif aussi.
Ouais. Mais ça, de toute façon, c'est faux, parce qu'en fait, j'ai juste du mal, je vais trouver là avec un peu de temps, juste de faire attention à bien séparer. Tu sais, parce que ça fait pas exactement comme j'ai mis exponentielle de ça, moins exponentielle de moins ça. Plus exponentielle de moins ça. C'est juste qu'il faut bien séparer quand ces produits, en fait, ils valent plus 1 ou moins 1. En gros, c'est pas toujours ça vaut plus 1 ou moins 1 dans la trace. Il faut juste faire attention à bien intégrer. Mais je pense que ça va marcher. Parce que tu vois, il se peut que là ça va le plus 1, là ça va le moins 1 et donc ça va donner moins 1.
Comment tu vas savoir parce que tes métriques elles sont.
Bah, en explicitant là. Ouais, mais tu peux, après, de toute façon, t'as des sommes.
Ouais.
Tu vois. Et je pense qu'il faut. Et là, donc, je l'ai fait un peu rapide pour voir, mais de toute façon, en sachant que c'était faux. Mais là, je pense que je vais juste pour avoir une idée au cas où. Mais je pense que ça va marcher. Parce qu'au fond, ces sommes, elles sont claires, tu vois. Et que ça va. Chaque terme est bien défini en étant plus 1 moins 1, plus 1 moins 1. Donc il faut juste bien ordonner les sommes, et je vais faire des trucs comme ça.
Est-ce que c'est possible qu'ils sont tous plus 1 moins 1
Oui. Chaque S alpha J vaut plus 1 moins 1.
C'est les deux valeurs possibles, mais est-ce que tu fais tout
Non, pas le produit. Mais le problème, c'est juste que...
Quand tu prends un vecteur S alpha, c'est sur un c'est toutes les valeurs sur un site.
D'ailleurs, je voulais te dire, il y a un truc, attention, S alpha J et S
Mais je l'ai réécrit bien sur mon truc que je t'ai envoyé. Enfin, mon avis. J'ai essayé de reprendre la notation de Raïm en fait dans ce que j'ai noté dans mes notes de cours.
Ah, ok, écoute, je continue à pousser ça tout ce temps. Et sinon, de toute façon, on prend ton résultat qui a l'air pas mal bien.
Il est interprété, il colle, tout de suite il colle quoi, avec ce que nous disait Obi, c'est juste ça. Après, ce qui est rigoureux. Et d'ailleurs, tu te rappelles quand il avait parlé à Teleg, là on l'entendait, il parlait de saddle point, truc là, machin. Saddle point, en gros, c'est la condition de station que je t'ai permis de minimiser. C'est juste pour minimiser en fait. Et je t'en viens d'arriver par rapport à ton paramètre d'ordre, donc soit Q, soit M, sauf que là, on n'a pas de paramètre d'ordre. Puisque dans le résultat final, je n'avais ni Q ni M. Et c'est peut-être, j'ai cette impression que je suis cru avoir. À un moment dans ce que j'ai fait, j'ai essayé de faire apparaître du Q. Enfin, ça s'annulait après le M sans être ça. Et donc, je ne sais pas pourquoi il parlait de saddle point. Donc, c'est peut-être pour trouver le ground state. Je me suis dit, c'est peut-être pour trouver le ground state, qui est le point qui minimise. Enfin, c'est même pas le point qui minimise l'énergie. Le point qui minimise l'énergie libre. Le ground state minimise pas l'énergie. Bon, bref, j'ai trouvé une